The systems that we worked with in the last section were all linear equations, whether linear meant a straight line in 2 dimensions or a plane in 3 dimensions, or even maybe a bigger situation where I had 4 or 5 or 7 equations and variables. But in this section, we're going to talk about nonlinear systems. In a nonlinear system, that means at least one of the equations is not a line. Okay, now when we start off, one of them will be a line, and we're also not going to go beyond two equation systems in this section. We could use the same methods that we used in the last section to solve these nonlinear systems, but I want to talk for a couple minutes about the number of possibilities with our solution sets. Okay, let's say that our system involves a parabola and a line. And so I want you to think for a moment, if you drew a parabola on your paper and a straight line on your paper, how many times they might cross. So here's my line. Maybe here is my parabola. And there, in this picture, would be two solutions to that system. Okay. However, there don't have to be two solutions every time. Notice if we move our line over here, there aren't any solutions. If we scoot our line maybe down right here, it looks like there's one solution. And regardless of how we turn, a parabola doesn't have to open up or down. It can open side to side. But no matter how we twist and turn and draw and move those lines, that line and the parabola, those seem to be the only three options. There's no solution, one solution, two solutions. I could spin my line around. Okay, we're back to one solution. Even if I slid it over here, there would still be one solution. Let me move those guys out of the way. Our options are two solutions, one solution, or no solutions. Maybe my system involves having a circle, and we've talked about circles, and maybe an ellipse. Okay, we didn't have enough time this semester, nor do we anymore, to talk about conic sections, but an ellipse is kind of like an oval. Our planets follow elliptical orbits. There are other things around us, okay, that follow that elliptical shape. Okay, so let's think about how many solutions we could come up with here. It looks like I could put them side by side and they don't intersect at all. So I could create a situation with no solution. Okay, maybe they could just kiss like that side by side and intersect at one point. Maybe I could slide it in kind of like this, and now there's 2 points of intersection on that ellipse. Or I could make Saturn like this, and I have 4 solutions, 4 points of intersection. Okay. Notice that if I slide just like this, now I've got 3 places where those 2 curves intersect. So if we make our list, we found a way to where they didn't intersect at all. We could make them cross once, or twice, or 3 times, or 4 times. Okay, any and all of those are possibilities, but no matter how I twist and turn and stretch and shrink, I don't really see a way that I could make them intersect more than 4 times. So what I'm going to tell you then in this section, the point of these doodles here in making these lists, is when I write down the system of equations out of my book, maybe here it is right here, I can't tell just by looking at the system how many possible solutions I'm going to have. Okay, if I know what shapes they make, then I might be able to visualize my options. For example, that one I just clicked away from is a straight line, and it is a parabola. And so we're either going to find out that they don't cross, or cross once, or cross twice, but not 3 times, or 10 times, or 12 times. But what I have to do is I have to trust in the algebra to lead me to the right number of solutions. So the two methods we talked about in the last section are substitution and elimination. Now with our linear systems, either one worked in any problem. If I wanted to use substitution every time, I could. If I wanted to use elimination every time, I could do that. But the reason I had you practice both is because here there are times when we can't use one or the other, at least not very easily or straightforward. I will tell you, and again, that's not to say that you can never use elimination on a system like this, but if one of your equations is a line, then usually substitution is going to be your most direct path to that solution set, whether they intersect one time or 10 times or not at all. Okay, so maybe I'll stay in blue. So let's look here and think about using substitution. And so that means I need to start by solving one of my equations for either x or for y. And I have four places I could start, at least in theory. Sometimes algebraically I can't take any path that I want. But if we look up here at the top equation, okay, if the author has already done some work for me, take advantage of that. Meaning the top equation is already solved for y, so I can drop that down here into that linear equation. Carefully drop it down. Okay, now if I wanted to solve the bottom equation for x or for y and go from there, I could do that as well. My tablet and I aren't getting along tonight. So if we have 2x minus y equals 2, we said in place of the x, I can put x squared minus x. Sorry, in place of the y, I can put x squared minus x. Don't forget about that negative sign out in front, because it not only belongs to the x squared, but it belongs to that negative x as well. From here, once I have my equation with only one variable, I'm going to solve it using whatever appropriate method applies to that situation. Here I have a quadratic equation, and with a quadratic equation, I like to get a 0 on one side first. Okay, I'm going to add everything to both sides. Everything to both sides. I'm going to move the x squared over to the right side and put my 0 on the left, because I like x squared to be positive. This 3x here, I'm going to subtract, and the plus 2 is already there. Then if I can factor the polynomial, I'm going to factor it. And if I can't, then I'll default and use the quadratic formula. I'll still write this step down, even though many of you will skip it and would be okay if I did. But here are our two values of x. Okay, x equals 2 and x equals 1. So then I know once, with my linear system, once I found a value for one of the variables, I took them back to the beginning and I plugged in and solved for the other one. So if I use the top equation, nothing special about it. It's just on the top, so that's where my eyes went. I plugged in 2 for x, and 2 also came out for y. When I plug in 1 for x, 0 comes out for y. So I always have to write as ordered pairs. I'm not going to make a list of a bunch of x's over here and a bunch of y's over there and make people guess which one go where. When I plugged in 2 for x, 2 also came out for y. When I plugged in 1 for x, 0 came out for y. Okay, I'm going to show you a picture of this in just a moment. I clicked over to Desmos real quick. Ready, go. And drew those two graphs. Here's y equals x squared minus x. And here is whatever the line equation was. I'll cheat. 2x minus y equals 2. And if you notice, they do in fact intersect at the point 1, 0, and 2, 2. And when you're solving these for me on a homework quiz or test, don't If you use a graph and tell me I looked at the graph and here's my points of intersection, you're going to get 1 point. I want to know and see that you can use the algebra. That's the skill we're trying to master and that I'm trying to assess. Okay, we can all use our eyes and computers to help us, okay, pinpoint those values, but what we're trying to learn is how can I do this algebraically? So this is what I want to see. Okay. In the next video, we're going to do some more examples, and we'll take it from there.